One now you can zoom in and out with this, and you can hold in this part way to
Okay.
focus.
Is it recording? Oh,
It's
yep,
recording right
it's
now,
recording.
yeah.
Okay.
So
Hey.
this,
So she definitely put that in her
No, I
face.
didn't.
That's like up next.
everybody,
Wait.
a moment of fame for Maria. This question, I'm going to go back to a couple pages before. Go to the back of the first page. This question was on a test last year,
You don't do it.
and I didn't
Yeah,
realize
sure, I
it was
can
so
do it,
hard until I
actually.
graded all the tests and people did badly on it. So I'm trying to make sure that I do a better job explaining it this year. So far, I think people are getting this. It's a complicated scenario involving somebody parachuting and pulling the parachute cord at some point during the fall.
Why is it's blurry?
What's
It's
it,
really
blurry?
blurry.
If you hold down on this part way,
Do you hold it there?
wow, look at that.
I know. Oh, there it
Oh
goes.
well.
Oh,
I don't know. Here, focus on the wall.
Like the zooms in, like
What's wrong with this
oh,
camera?
that's good.
he was
Yeah.
Okay.
It's just bad. Maybe it's because I don't know what might be constant. Maybe if I turn.
people who are like,
Nah, we'll just go with it. Tell me if it gets real blurry again.
Okay.
Can you two be quiet? I'm going to read the scenario and then I'll try to explain in more detail. So the first table below provides information relating to a parachute jump. There's some mistakes in here too. A parachuter steps out of an airplane, that should just be all one word, begins to fall and subsequently reaches terminal velocity. If you're falling from the sky without a parachute, do you remember how fast I said you might get going? What is terminal velocity of a human falling from the sky? Did I ever tell you this? Maybe not. It's about 120 miles per hour. If you fall like this, maybe a little slower. If you fall like this, maybe a little faster. But if you're knocked unconscious and you're just falling like a mannequin, probably about 120 miles per hour. And so after reaching that terminal velocity, the parachute deploys. So somebody they pull the cord. It's a woman, pulls her chute. The chute takes a few moments to open. They don't open instantaneously. And soon after that, the parachute reaches a new terminal velocity, which is going to be a slower terminal velocity because now the chute has more surface area and it's going to slow the person down. Minutes later, the parachute lands on the ground. You know, I've been going over these questions in other classes. I'm going to skip these. I think these are muddying the water and maybe I'll regret it later, but let's just not cross them out, but let's skip them. So you have a timeline like this, and then the goal is to fill in this chart with all the right information. I've made some diagrams over here to try to clarify what's happening there. Maria, can you zoom in on this?
I got you.
All right, am I blurry?
No.
Okay, so here's what's happening. At 0 seconds, somebody steps out of the plane. I regret that it's a plane. It should be a hot air balloon, because or even just a cliff face that they're stepping off of. Because the plane's moving sideways, so really that adds some velocity to this person. But forget about the plane.
It's stalled
They're just-
straight up.
Okay, it's stalled. They somehow made the plane hover. Oh, it's one of those
It's one of those stunt planes.
Osprey, or I think
Or
there's one called an
PPT.
Osprey where it can rotate its propellers down. Okay. So anyway, person steps out of the plane, they're not moving yet. It's like me, if there were a chasm right here, I could step out and I'd have 0 meters per second, then I'd start to speed up. And they speed up, speed up, speed up. According to the timeline, at 15 seconds, the parachuter reaches a first terminal velocity. So that's right here. They're going as fast as they're going to be going unless they do something else. And at that point, it's terminal velocity because the air resistance pushing up is equal to their weight pulling them down. And since those two forces are balanced, there's no net force, so they're not going to accelerate anymore. So they stay at 60, 60, 60, 60 until 50 seconds when the parachuter pulls the cord and the chute deploys. So here the chute starts to come out. What's that going to do to the speed? Slow them down. They're going to begin to slow down in how fast they're falling. And then at 60 seconds, the parachute has fully deployed and they reach a new terminal velocity of 7 meters per second. And then once they're at that next terminal velocity, the chute stays open, they just float to the ground 7 meters per second. all the way until the 600-second mark. So from here to there, that's about 5 more minutes. No. Yeah, 9 more minutes. 9 minutes to get to the ground. So they're going faster, 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 reach terminal velocity, stay at terminal velocity, pull the chute, start to slow down, slow down, slow down, get to this new terminal velocity, and then stay there until they get to the ground. Kind of with me? Maybe? It's confusing because of 2 terminal velocities, and then we're going to do some stuff here. Maria, I can make a copy of this. It's kind of hard to write the video. Okay. The goal is to fill this out. To do something else funny. Did you point it at yourself again?
No. No.
We've got
Put it on the
at
beautiful
a time of
part
0
there.
seconds. We've got the mass of the parachuter. We need the weight. How do we get the parachuter's weight? You weigh them. But without being able to weigh them, we've got the mass. That we can calculate the weight based on the mass. What? Force. Weight is the force of gravity, and gravity is just the. Here's weight.
It's okay, we forgive you.
And any force is the mass times the acceleration. In this case, it would be the mass of the parachuter. And the acceleration is just the acceleration of gravity, negative 10 meters per second squared. So the weight of this parachuter would be 1,000 what?
Fill out mine too.
Newtons. And really, it should be negative 1,000 newtons because it's downward and negative 10. The parachuter weight, 1,000
Being professional
newtons.
movie
And I
maker.
didn't ask you to, some of these you can say I put plus direction on there. I should have done it on weight. Let's add it in. But just use an arrow. I found that using arrows on this is better. The weight of that parachuter is pulling her down with a force of 1,000 newtons. Now let's jump over to the right problem. What's the speed of the person at the moment they start stepping out of this hot air balloon? What? 0. And you're just going to have to use common sense, and I won't make fun of you if your common sense won't help you here, but somebody tell me, if you're moving at 0 meters per second, what's the force of air resistance pushing against you? 0. There's no wind pushing on you if you're not moving. So there's no air resistance yet. And I'm going to draw a little picture here. Here's the person. This is the force of gravity pulling them down. This is their weight. This is the force of air resistance pushing up. What's the net force in that case? 1,000 newtons which way? Down. And you could have probably told me this one before we did any of this, but what would the person's acceleration be if there's no air resistance? No air resistance is like free fall. So what's your acceleration when you're in free fall? Negative 10 meters per second squared. And I'm just going to write 10 meters per second squared, but I'm going to use an arrow. Wherever I have a downward arrow, you could just put a negative if you'd prefer. But I think for this, it's good to use arrows. You could have used this formula. You could say acceleration equals the net force over mass. This is the net force, negative 1,000 newtons, divided by the parachuter's mass of 100 kilograms, and you would get 10, or negative 10. Any questions? Do stop if it doesn't make sense. You're going to get a chance to try this on your own in a minute. So at the 10-second point, we're right here. We're between the time when the parachuter steps out of the plane and when the parachuter has reached terminal velocity. So this person is still speeding up. There's no way you would know the velocity of the person if it wasn't given in the question. So it's given in the question. They're not quite up to the 60 meters per second. And there's no way you would know the force of air resistance if that weren't given. But that's all you need. You can do the rest. What's the mass of the parachuter? Unless they've gotten sick or scared, both of those things could account for a little loss of mass. It should be 100 kilograms. Air sickness might have made them lose a little bit. Fear could take a little bit away from them. Or so I've heard. I've never lost mass from fear myself. And so what about the parachuter's
Oh, 'cause
weight?
he threw
Is the
up.
weight any different than it was? No. In order for the your weight to change, you either have to change your mass or change gravity, and neither of those is really happening. If you want to be really picky, you could say you're getting closer to the Earth, so gravity's getting stronger, but that's negligible. All right, so parachuter weight is the same. 1,000 newtons is pulling this parachuter downward. I'll draw a little picture for this. 1,000 newtons downward. And the question tells us that now that they're going faster, now they're going 45 meters per second, there's an 800 newton upward force from air resistance. So what is the net force? 200 which way? 200 newtons downward. And now we need to get the acceleration. So if you have a net force of 200 newtons downward, and your mass is 100 kilograms, how do you calculate acceleration? What? Force over mass. It's using F equals ma, but it's just rearranging it to that formula. So I'll just write it over here. If the net force acting on the person is 200 newtons downward, call it negative 200, divide that by 100 kilograms, I get 2, what would the units be for acceleration? Meters per second. And this is negative, so on my chart I'll just write 2 meters per second squared and have a downward arrow. 45 seconds. Looking up here at this chart, we're right in this zone. At 15 seconds, she reached her terminal velocity. At 50 seconds, she pulls a parachute. At 45 seconds, she's right in between there, between when she reaches terminal velocity without the chute and when she pulls the cord. So that tells us all we need to know to figure out her velocity, her speed. What is her speed?
45 minutes.
What's that?
45 minutes.
Not 45. It's 60, yeah. It's so when it was 45, that was at the 10-second mark. She didn't really reach her terminal velocity until 15 seconds. That's when she gets to 60. She's going to stay at that terminal velocity. She would hit the ground going 60 meters per second if she didn't pull her chute. But as it is, she'll stay at that same velocity until the 50-second mark when her chute deploys. So her speed is 60 meters per second. You know what this is going to be again. What's her mass? 100. I'm going to just draw some little lines down. It stays 100 kilograms the whole time. And her weight stays 100 or 1,000 newtons the whole time. Now, let's see. Ooh, actually, I'm going to write in her weight. You don't have to, but it's nice to have that number here. Because now I can, it'll help me find this. It'll help me find the air resistance. If you're at terminal velocity, that automatically tells you which of these things. 2 of these you can just fill in right away. If you know somebody is at their terminal velocity, then Tyler, which ones?
You know the air resistance is equal to the parachuter weight, and that the acceleration is 0.
And the net force is
Oh, 0.
0. So if you're at terminal velocity, I'm going to write TV over here. If you're at your terminal velocity, that means whatever the weight is pushing you down, that equals the air resistance pushing up. So in this particular case, if the person's weight is 1,000 newtons pushing down, then the air resistance has to be 1,000 newtons pushing up. Terminal velocity means it's terminal. Terminal is the end. Your velocity doesn't change after this point. So there's 0 acceleration. And if there's 0 acceleration, there's no net force. And if there's no net force, these two have to be the same but opposite one another. So this upward force of air resistance has to be 1,000 newtons. So any of these where they're in the range where they're at the terminal velocity are going to be easy. Blaine?
I'm kind of confused as to why, if the force pushing up and the force pushing down are equal,
While you're still moving?
Yeah.
It's trying to think of a good example. If we were at the ice rink, it might be easier to demonstrate. If you get somebody moving across the ice on this hovercraft, they're gonna lose a little bit of velocity, but they're pretty much gonna have a constant velocity. And once you let go, there's nothing pushing them, except maybe a tiny bit of friction. So to accelerate them, if this is the person, I give them a push, and then I stop pushing. There's no force acting on that person whatsoever. But they keep on moving because they have inertia or momentum. And then if so the fact that they're moving doesn't mean that there's a force pushing them. If I'm falling down from the sky and I'm falling at a constant rate, that doesn't mean I've got a force pushing me downward. It just means I'm continuing on. That's not a very good.
I kind of.
Do you have a good way to explain it? Yeah, an object's in motion stays in motion. I could say Newton's first law, but maybe picture a car that's moving down the road. If you get in your car and you want to go as fast as you possibly can, have you ever done that?
No.
Okay, all right. Well, anyway, if you decide you just are feeling somewhat suicidal and adventurous, and you push the accelerator all the way down as far as it'll go, and you hold it there, and you're on a straightaway, and you just go as long as you can, will you keep accelerating forever? Assuming your engine doesn't blow up, are you going to keep going faster and faster and faster? No, you'll get to some speed where, I can't tell which is the front of this car and the back. You'll get to some speed where the motor is pushing forward and friction is slowing you down. Just friction from the air pushing on you, friction from the wheels, and friction from the road. And you'll get to some point where those things will be balanced. And at that point, your car won't go any faster. Let's just say the motor is producing 10,000 newtons of force, and friction is pushing you back with 10,000 newtons of force. And you're going 120 miles per hour in your car. It'll just stay at 120 miles per hour until, let's say, you have a little, some kind of an air tank, and you open up the air tank and it starts to shoot some air out, and that gives you an extra boost. So now you have 10,200 newtons of force. Then you start to accelerate again. But as you accelerate, you're going to go faster, and the air resistance is going to increase, and the friction is going to increase, and it's eventually going to catch up to your motor force. And then you'll just stop speeding up again. You won't stop. It's not like you hit a wall, but you won't go any faster.
Okay.
And if suddenly you hit a headwind and this bumped your air resistance up to 12,000 newtons, then you're going to have a net force backward. It doesn't mean you're moving backward. It just means you're going to start to slow down. It's going to accelerate you the other way.
Okay.
So the net force is talking about acceleration, not movement. So in the case of this next one, normally I'd let you try this, but I want to do this next one because I think it'll help clarify this a little bit. In this case, at 55 seconds, between 50 and 60, the parachute deploys, but at 60 seconds, terminal velocity is reached. This is before the parachute has fully opened. This is before the person has slowed down as much as they're going to slow down from the parachute. They have a 1,000 Newton downward force and a 1,600 Newton upward force. So that's going to give you a net force of what? 600 in which direction? Up. And the acceleration, you can calculate the acceleration. It's that net force over the mass. Net force of 600 divided by 100 gives you 6 meters per second squared. Upward. So this person is accelerating upward, but they're moving downward. So the fact that they're accelerating upward doesn't actually mean that the parachuter goes back up in the air. It means that what's happening to this speed?
Slowing down.
It's going to get to be a smaller and smaller and smaller speed. So you can have zero acceleration and you can be moving downward. You can have positive upward acceleration and you can be moving downward. All those things are okay. Selena, is that,
Yeah, that
all
makes
right, it's
sense.
still, I don't.
No, I get it.
I did a bad job there, but
Oh,
hopefully in the end
fine.
you got it.
Thank
So
you.
this last part, the 150-second thing, since the video's going, let's do it together, but ordinarily I'd have you do it. At 150 seconds, right in here, what's going on there? This is a special time in the parachuting fall. Tyler, what's going on here?
Yeah, so that they're at terminal velocity with their parachute deployed, so they're going way slower than they would, or than they were.
Right. Every moment from 60 seconds all the way until the end, they're at terminal velocity. They reach it at 60 seconds. This becomes the velocity. It stays that same velocity all the way down. So they were at terminal velocity 1 here at this one. They're going to be at terminal velocity 2 at 150 seconds. And terminal velocity, if we know they're at terminal velocity, then we know the acceleration. What's the acceleration? 0. They're not accelerating anymore. They're still falling, but they're just falling at a constant speed. If they have no acceleration, is the net force pushing up, down, or neither? Neither. There's no net force. And if there's no net force, then this 1,000 Newton downward weight has to be counterbalanced by 1,000 Newton upward air resistance. And the very last thing, what's the person's speed? 7, and we could tell that from the chart. So now try the one on the last page. Give that a shot.
Can you go back?
Yeah, I can go back.